Hello everyone, this is Team 2, my name is Julia and my teammates are Peter, Alexander, William, Zonda and Joseph. This is our interim presentation for ME 452 and ISD 528. We decided to analyze and redesign an electric kettle. Electric kettles are commonly used to quickly boil water for a variety of culinary applications. The main features of the kettle are its ability to maintain hot water temperature and disconnect from the heating element for efficient pouring. They are really cheap and convenient for everyone. That's the reason why our primary customer group are families in residential settings who used it in everyday basis to prepare hot beverages or food. The secondary customers are employees in communal office settings who tend to make their own cups of coffee or tea.
We began with functional analysis system technique, otherwise known as FAST diagrams. So the task function is to heat the liquid rapidly in our case, and to do so requires the primary basic functions of holding the liquid and boiling the liquid. Holding the liquid, to do so requires allowing input of liquid into the device and then containing this liquid for subsequent boiling. Boiling, meanwhile, requires heat being provided to the device and directing this heat into the liquid itself. So we can assure dependability by avoiding burns, and we can assure convenience by stabilizing the base, controlling pouring of the liquid, and being able to grasp the device efficiently. We can enhance this product by maintaining temperature, and pleasing the senses is also the final requirement for our product.
Next, using a fishbone diagram, two feasible assembly sequences were determined in order to understand the most efficient method to construct the electric kettle. The main housing of the electric kettle is the first part in both sequences, as it is the main part to which all other components attach. Two subassemblies are featured in sequence 1, however only one subassembly is featured in sequence 2. This is because sequence 1 is more of a parallel assembly, whereas assembly 2 is more serial. The two assembly sequences were then ranked on a scale from 1 to 3 according to the criteria in the leftmost column of the table: ease of transferring and handling, ease of locating parts, ease of fastening joining, ease of testing subassemblies, and ease of assembling in parallel. Note that a higher score represents a more desirable assembly in terms of that particular criterion. After the individual scores were added, we found that sequence 1 is better in terms of the 5 criteria listed in the table.
This slide shows our function component mapping matrix. Most of our parts only apply to a singular task function, or in the case of the button, no task functions. This could imply the need for a redesign to reduce the number of parts later on.
This is the BOM for our electric kettle design. This was made to get a better understanding of what it will cost to actually manufacture and also assemble our electric kettle. Now, some of the assumptions we made when developing this bill of materials was, first off, that our yearly volume would be 10,000 units. Second, that the tooling life for each tool would be 100,000 units. Operator costs, in the United States, we assumed to be about $20 per hour. And then for our injection mold, the operation cost was about $50 per hour. So, lastly, with all the tooling and material costs, these are based off the geometry and the dimension from the actual CAD model of the electric kettle. So one thing we also excluded was the manufacturing assembly process for purchased parts, such as the fuse, the power plug, and the off-and-on switch. These are things that are going to be purchased from external suppliers, so we didn't really include those manufacturing assembly processes for those. And with all these assumptions and things taken into consideration, the total estimated cost of our electric kettle was $69.07, which puts our electric kettle in kind of the higher end market, kind of higher quality electric kettles that are currently being sold.
We next looked at the product family by performing a function comparison between the two groups. Like we mentioned before, the first group is more for households, and the second customer group for a commercial or office appliance. Because of this, they have similar functions, except the only difference is for the office appliance, it needs to be able to hold more liquid, since it will be used more often. Similarly, most of the parts are the same except for the main housing. And the main housing is only different because it needs to be able to hold more liquid for the office appliance. Looking at the part itself, we made these changes by only having the secondary product variant have a larger height than the primary, thus allowing it to contain more water. Looking at the common interfaces between the main housing and the other parts, we have the handle interface and then the lid and base interfaces, and these do not change at all between them.
The diagram on the left shows our chosen assembly sequence for our primary and secondary products. We were tasked with delaying the differentiation and assembly between our primary and secondary products. We identified that the only way to do that was to delay the introduction of the main housing unit. There's the possibility to even delay differentiation further between our product variants by delaying the introduction of the main housing unit even further.